Welcome to the webcast dedicated to the absolute quantification of oligonucleotides and the POPS ratio determination for a phosphorothioate using ICP-MS. As any other API, an oligonucleotide needs a quantification method. There are several classical relative methods like chromatography, followed by MS or UV detection or PCR. But all these methods require calibration with the standard solution of the oligo to be assayed. However, unfortunately, such reference material with a certified content is almost never available. So, such methods are not applicable in most cases for assay of the oligonucleotides. In comparison with relative method, the absolute quantification is a method that does not require a reference substance, in this case the reference oligo. Here are some methods that allows absolute quantification. UV spectroscopy is one of them, but it requires knowledge of the molar extinction coefficient that is theoretically calculated on the basis of the absorbance of the constituent nucleotides. Such estimation has been shown to produce a bias of more than 10%. Nucleotides can be analyzed after hydrolysis with a phosphorodiesterase. Might be difficult for modified oligos. The nucleotides that are freed are now analyzed using HPLC or UPLC with UV or MS detection. One can use nucleotides or deoxynucleotides as standard, or even label standard if isotope dilution is used. Such determination has an accuracy of 90 to 110% with an RSD of 5 to 10%. With an additional hydrolysis step using an alkaline phosphatase, one can conduct a similar analysis with nucleosides. So, for the quantification of an oligo, there is an urgent need for a fast and accurate generic method that will not require the reference oligo. And we will show that in this webcast that ICP-MS can be a solution. Needless to say that all oligonucleotides contain a lot of phosphorus in their backbone. So, the determination of phosphorus content will allow oligo concentration determination, provided the stoichiometry, in other words, the molecular formula, is known. The oligos may be digested to convert all phosphorus of diester bonds into phosphate ion that can easily be determined by ICP-MS. So the number of moles of oligo in the sample is equal to the number of phosphate determined by ICP divided by the number of phosphodiester bonds. All you need to know is the phosphate concentration and the oligo's molecular formula. Another interesting feature is the POPS ratio determination for the phosphorothioates. You all know that most oligos are chemically modified to improve resistance to in vivo enzymes. And one of the most frequent modifications of the phosphate backbone is the substitution of one or several PO bonds by a PS bond to yield the so-called phosphorothioates. Due to the stepwise synthesis process, even a highly efficient sulfurization process, like 99.7%, may result in a high amount of impurities, I mean oligo lacking 1 PS. For example, a 15-mer oligo with 14 phosphorus linkages will contain only 95.9%, corresponding to 0.997 to the power 14, of the real full PS oligo, plus a lot of impurities. There are 14 possible ones missing 1 PS bound, plus a lot of diastereoisomers. However, as regards the regulatory quality aspects, the purity of an oligo needs to be characterized. In the particular case of a phosphorothioate, a missing substitution may play a role in the potency and the in vivo stability of the oligo versus nuclease activity. So, the POPS molar ratio is a critical quality attribute for therapeutic oligos. Usually, such ratio is measured by phosphorus NMR, but such technique is not really available in pharmaceutical labs. In addition, it is slow, sequential, and lacks sensitivity. De Ridder and al. Said in the Handbook of Analysis of Oligos that a typical oligonucleotide phosphorus NMR experiments may need 12 hours or more using a 10% solution in deuterium oxide. That is a high concentration that is needed. Another way to determine the POPS molar ratio is strong anion exchange chromatography, but it is complicated by the large number of possible impurities having one phosphodiester bound. There are several possible positions for the missing PS, and in addition, there is presence of diastereoisomers. But ICP-MS may be used not only for the sensitive determination of phosphorus, but also for that of sulfur, virtually at the same time, allowing simultaneous quantification of phosphorothioate oligo and the determination of its POPS ratio. Some words about the ICP-MS determination of sulfur and phosphorus. These elements have a high ionization potential, more than 10 eV. That means that they show low sensitivity in ICP-MS. In addition, there are many polyatomic interferences for all isotopes of phosphorus and sulfur. For example, the 32 sulfur, that is the most abundant isotope of sulfur with more than 95%, has a very large interference due to the oxygen. Remember that we introduced in the ICP-MS water solution, meaning that you have thousands of times more oxygen than sulfur. And the same problem occurs for all other isotopes of sulfur and phosphorus. Fortunately, a new instrument is now available, the ICP-QQQ. It's a triple quadrupole made by Agilent that allows the operation in mass shift mode. For those who are familiar with molecular MS, it's a MRM-like mode. The first quadrupole is set at mass 32, allowing only ions with mass 32 and a single charge to go through it, like sulfur or the oxygen. These ions enter into the collision cell where we introduce some additional oxygen to react with the sulfur to produce sulfur oxide with mass 48. The third quadrupole is set at mass 48 to allow only sulfur oxide to go through to the detector. Oxygen itself does not react with the added oxygen and is rejected by the last quadrupole. Such configuration allows the elimination of virtually all interferences and shows very high sensitivity. In fact, the LOQ is only governed by the residual sulfur in reagents and solvents. If we want to have simultaneous determination of sulfur and phosphorus, then we will set Q1 and Q2 alternatively to 3248 for the sulfur determination or 3147 for phosphorus. The fast switching allows simultaneous measurement of sulfur and phosphorus as their corresponding oxides. So the same situation is valid for phosphorus. We set the first quadrupole to mass 31. Phosphorus reacts with oxygen in the reaction cell to produce ions with mass 47 that are allowed to go through the last quadrupole to the detector. So we have seen that polyatomic interferences can be removed, but Nebulization efficiency is another problem. Remember, this is an ICP-MS instrument, meaning that the sample is introduced through a nebulization device. Nebulization and transfer efficiency are not equivalent for small and large molecules. As we use calibration solution made of sulfuric or phosphoric acid, for a good accuracy, we need sample digestion to have all sulfur and phosphorus as sulfate or phosphate ions. Such sample preparation is quite easy using a microwave system. Into a disposable glass tube, we introduce an amount of sample corresponding to about 0.5 milligram of phosphorus, meaning something like 6 milligram of oligo. We add an internal standard solution of yttrium and concentrated nitric and hydrochloric acid. Then we run the microwave digestion program, and finally we transfer and dilute the sample to 50 ml with water, making the sample ready for ICP-MS determination. Here are some data regarding the digestion protocol. We use an ultrawave from Milestone as the microwave digestion. After addition of nitrogen into the digestion cell, we heat the sample up to 220 degrees in about half an hour, and we keep it at the same temperature during the same time. After cooling and pressure release, the sample is easily diluted and ready for ICP. The reagents that we use are quite classical. We need just a phosphorus ICP standard and a sulfur ICP standard. Both are diluted solution of the corresponding acids. We add a very classical yttrium plasma internal standard that one can find easily. And we use also an additional compound that is the ethyl thiophosphate potassium salt as a QC control. We'll speak about that later. Plus nitric acid and hydrochloric acid of trace metal grade. Here are some parameters for the ICP-MS. You see that we use a high RF power. Remember that phosphorus and sulfur have high ionization potential, so they need high energy. The other parameters are quite classical. You can find here the addition of oxygen in the reaction cell and the different setting for phosphorus, sulfur, and yttrium of the Q1 and Q2 quadrupoles. Here is the ICP-MS calibration using phosphorus and sulfur solution. You can see that we have very good linearity with coefficient of determination greater than 3.9. Let's speak about method performance. First, for the phosphorus determination, we have been looking for an oligonucleotide with a certified accurate concentration, but it was not available at the time of method development. The accurate concentration of an oligonucleotide remains a big problem. So to assess the performances of the method, a more characterized sample, DTP, was taken as a model compound and digested as a sample. So this is a molecule containing phosphorus and sulfur in a known ratio. First, as regard the phosphorus determination, so the absolute quantification, the accuracy and precision were evaluated by digesting different amounts of DTP, resulting in solution containing 0.2 to 0.6 millimole of phosphorus per liter. 3 determination for each level, and you can find here the average accuracy measured as the recovery of phosphorus. All of them are close to 100% with a very good RSD of less than 0.5%. Here is now the method linearity. This is not calibration, but a true method linearity with the experimentally measured phosphorus concentration versus the theoretical one. Once again, we have very good coefficient of determination and a slope that is close to 1. Method performance for the PO-PS ratio determination. In order to demonstrate the performance of the method, different solutions were prepared with a constant phosphorus content and a variable sulfur one, resulting in different PS molar ratio ranging from about 1 to 46. You can find here the experimentally determined PS ratio and the calculated accuracy. That is once again close to 100%. The RSDs are very good, less than 0.6%. Once again, the method linearity with the experimentally determined PS ratio versus the theoretical one. Very good coefficient of determination and a slope close to 1. Here are some additional data regarding method performance. As we had some oligonucleotides in stock in the lab, we decided to analyze them using our method. You can see here the different samples tested with a number of bases ranging from 20 to 23, O-methyl modification, or even a cholesterol addition. Most of them are full PS, except that one that has only 6 sulfur. In addition, you see here the diethyl thiophosphate used as a QC control. Here are the results of the ICP-MS determination. So this is absolute quantification. And you see that the diethyl thiophosphate has a recovery of about 100%. In comparison, here are the data obtained on basis of the theoretical molar extinction coefficient. And obviously, there are large differences between the two determinations. But remember, that one is based on a theory. Once again, the RSDs are low, less than 2%, because it was 3 determinations for each sample. Here are now the results of the PO-PS ratio for the same sample. Most of them are full PS, so the ratio are 1. Only this one has 6 sulfur, meaning that the ratio is 3.8. The experimental results are reported here, also for the DTP sample, and you can easily see that the accuracy is really very close to 100%, with very good RSDs showing once again that the method has a very good precision. Interesting additional feature is sodium determination. Oligos are polyanionic compounds, so a counterion must be present, and very often it is sodium. This method is easily adapted. We can use the same digested sample solution with an extra dilution if necessary, and we can easily determine the sodium concentration using the same ICP-MS, eventually simultaneously. So, the main method features are a very good sensitivity. We only need 5 to 6 milligrams of oligo for one determination. It shows a high reproducibility with the RSD less than 2%, great accuracy, less than 3% bias for the absolute quantification, and less than 1.2% bias for the PO-PS ratio. As we digest the sample, the same method can be used for any oligo. And you can determine all these oligos or even messenger RNA using the same method. We just need very common reagents and standard. We don't need the reference oligo. And the method is a high throughput one. Many samples may be processed and analyzed on the same day. However, as the other absolute quantification method, this one is not suitable for the determination of impurities and degradation products, nor for a mixture of oligonucleotides, nor for the evaluation of an oligo stability. Obviously, phosphorus will never disappear. But it is nicely suitable for the assay of a single oligonucleotide presented as a lyophilizate or a solution, obviously without a phosphate buffer. It is suitable for the simultaneous accurate determination of the PO-PS ratio if the sample is a phosphorothioate. It's quite suitable for the sodium determination as a counter-ion, or also for the residual sodium chloride after desalting by ion exchange. It can be used for the accurate determination of the oligo concentration in a solution aimed to become a standard. And finally, for the accurate determination of the true molar extinction coefficient. So, it is an excellent orthogonal method with regards to the nucleotides or nucleosides analysis versus the theoretical molar extinction coefficient calculation, or versus the phosphorus NMR. And Quality Assistant is proud to offer these services to its customer. It may be the assay of a single nucleotide, either as a drug substance or a drug product, simultaneous determination of sodium if needed, PO-PS ratio for a phosphorothioate sample, the accurate molar extinction coefficient determination, or the accurate assay of a reference oligonucleotide. Thank you for your attention. If you have any question, please feel free to send it to Arnaud de Lobel, and you have his email address here. Thank you again.